For most of human history, shaping iron required intense dynamic force. Raw metal was heated until red hot, then compressed and fused blow by heavy blow. Standing in the Qutub Minar complex in New Delhi is an object that appears to have bypassed the standard limits of that solid-state process. This is the Delhi Iron Pillar. It stands over 23 feet tall, weighs approximately 6 tons, and consists of iron with a purity of 99.72%. It has remained in this environment for 16 centuries. Its construction dates to the Gupta period, around 400 CE. This was a millennium before furnaces capable of producing liquid cast iron were operational in India. Despite 1,600 years of constant exposure to monsoon rains and high humidity, the pillar shows negligible atmospheric corrosion. It is a wrought iron structure containing significant slag impurities, which typically accelerate decay. In modern metallurgy, this is a chemical contradiction. Heterogeneous iron filled with entrapped slag usually suffers from severe localized galvanic corrosion, as the impurities act as internal sites for rapid oxidation. Modern archaeotechnology allows us to examine the pillar's internal logic. By analyzing the physical structure and the electrochemical behavior of its surface, we can see how it utilizes its chemical flaws to survive as a complex assembly. Understanding the Delhi Iron Pillar requires looking past its monolithic appearance to identify the specific mechanical and chemical systems that have preserved it since the 4th century. This schematic reveals the full scale of the pillar, divided into distinct functional zones. A 5-foot section of the main body remains rough, anchoring the pillar underground. The top 3 feet and 5 inches comprise the decorative capital, the most intricate component. To build this, the smiths faced a strict technological constraint. Iron was produced through the solid-state reduction of ore over charcoal. It remained solid throughout the extraction process and could never be poured. To create large objects, they employed forge welding. Small lumps of hot iron were stacked and struck with enough force to fuse the metal together while still in a solid state. While the 20-foot main body was built using a vertical forging technique, stacking and hammering lumps sequentially, the capital's complex geometry suggests a different approach. The shape of the capital is too intricate for a single forging event. Its geometry indicates a multi-part construction, showcasing the sophisticated limits of ancient solid-state joining. This dimension diagram shows that the capital's components follow a pre-calculated plan. The measurements are uniform, indicating the parts were forged to a specific design rather than shaped by eye. This lower section is the reeded bell, often called a Purna Kalasa design. Although appearing solid, the bell is built from modular iron bars. Each unit consists of a single long rod bent into a U-shape, flanking a straight central rod. 20 of these assemblies are arranged circularly, creating the primary structure. These 60 rods travel upward, converging at the top neck of the bell. Because the diameter is wider at the bottom, gaps naturally occur. The builders inserted 20 shorter filler rods to close these spaces and complete the visual pattern. This required forging 80 distinct modular shapes to exact specifications before the final assembly could begin. The resulting bell is the product of modular geometry, using multiple pre-shaped components rather than carving a single mass. Above the bell, the capital features a slanted reeded section, where 52 rods are positioned at a 45-degree angle. Close visual observation of these rods shows flattened facets and hammer marks on their curved surfaces. These marks are the physical evidence of forge welding. They are the deformations left behind by the dynamic hammer strikes used to fuse the rods to the base. At the junction where straight lower rods meet slanted upper rods, there are deliberate offsets. These were engineered to ensure a tight physical match between the two layers. Chemical analysis of the gaps between these rods has revealed traces of lead. The lead served as a solder, used to fill small voids and seal the joints within the assembly. The presence of lead solder alongside hammer-deformed iron indicates a multi-material engineered joint, built in distinct phases. The capital is topped by a series of heavy, circular iron discs. These discs transition geometrically, moving from a 16-sided disc to a thicker 20-sided disc and back to a 16-sided disc. These discs are structurally locked together. Each features half-inch thick projections that slot into the surface of the next, creating a mechanical bond. A hollow central cavity runs vertically through the center of this entire stack. This central channel allowed for a shrink-fit assembly. The discs were heated to expand, dropped over a hollow iron pipe, and allowed to cool. As the metal contracted, it gripped the pipe, locking the components into a single unit. This central pipe was then connected to the massive main body of the pillar, using an iron insert. The entire upper capital is an assembly held together by interlocking geometry and thermal contraction. With its mechanical structure understood, we can address the chemical paradox. Why hasn't this phosphorus-heavy, slag-filled iron rusted away over 16 centuries? Mixed potential theory provides the model for this survival. When we look at a microscopic section of the iron, we see slag inclusions embedded in the metal matrix. These slag particles do not act as points of failure. Instead, they function as efficient cathodic sites, drawing the electrochemical reaction away from the iron. This rapidly polarizes the metal, forcing it into a passive state, building a dense protective film of delta FeOOH and lepidocrosite. The chemical analysis shows that the protective film has shielded the pillar for 1,600 years because of the slag impurities, which catalyzed the formation of the passive layer. The Delhi iron pillar remains standing today as a record of ancient technological capability. Its construction involved modular planning, solid-state impact welding, lead soldering, and thermal shrink-fitting. Modern industrial methods rely on the transition of iron to a liquid state for casting. The Gupta-era smiths achieved a similar complexity through intensive labor and solid-state joining. In a final chemical irony, the high phosphorus and slag content native to charcoal smelting provided the electrochemical environment necessary for the pillar's long-term survival. The Delhi iron pillar is a physical demonstration of advanced ancient engineering, standing as a testament to the sophisticated metallurgical knowledge of the 4th century.